Hi, my name is Bahadur Ahmedov. Welcome to the course of Probability and Statistics. In this lecture, we are going to discuss the likelihood functions, and we are going to solve a couple of problems in order to estimate the population's parameter using so-called maximum likelihood estimation method, MLE method. And before we do this, we are going to briefly review what does it mean, the likelihood function. So probably you have seen about the probability mass function, which is going to tell us the distribution of the outputs for the random variable. So if you have got the random variable, which is going to take the two outputs, for example, 0 and 1, with the probabilities, for example, 2 over 3 and 1 over 3, we can write down the program in R or in any other programming language, which is going to generate the outputs, zeros and ones, depending on this probability distribution function or probability distribution table. For example, you can just write a program which is going to generate you 0, 1, 1, 0. Oh, this is very much similar from the real world problem of tossing a coin. For example, you've got a coin which is not fair. It means that probability of getting heads is equal to 2 over 3 and probability of getting tails is 1 over 3. And you can just toss this and getting some results. Heads, tails, tails, heads, for example. And then now the problem is most of the time in the real world, we obtain the data and we don't know the parameters. For example, let's assume that you've got this data, zeros and ones, and actually you don't know how this data has been generated, or you would like to know, hey, what would be the parameter in my table, for example, here. So the probability of, so the 0 and 1, what is this parameter? 1 p and 1 minus p. So which value of this p is going to generate me this data? So basically, if you have got data, we are basically looking for the parameters of the distribution tables, which could generate us, which most likely generate us this data. This is what does it mean, the likelihood functions and maximum likelihood estimations. And we are going to, I'm going to explain you how it works in an example. So let's say I've got a coin which is tossed 50 times and resulted 30 heads and 20 tails. So find the likelihood function for the number of the heads, for example, first of all. So, so when you toss a coin, and get the heads and tails, the number of the heads or number of the tails have the binomial distribution, right? So if you assume that getting a hat is equal to the p and getting heads is p and getting the tails is 1 minus p is getting the tails, then probability of getting 30 heads for some given p is going to be equal to the combination of 50, 30, p in the power of 30, and q in the power of 20. So here q is equal to 1 minus p in the power of 20. Well, this function is called the likelihood function, which is very much similar to the binomial distributions function, right? So while in the binomial distribution, we are not given the output. So we are given, hey, so for some output, I can calculate the probability. So 50k, p in the power of k, and q in the power of 50 minus k. We are given p and q. I would like to know, hey, what is the probability of getting this output? And while in the likelihood function, I'm asking myself or you the different question. I'm asking you, hey, for what value of this p, most likely I'm going to get the 30 heads, right? So what is the probability? So for what value of the p, I will get this number, so 30 heads. In order to do this, I need to maximize this function. So basically, what I'm going to do is I would like to find the value of the p, which would maximize me this function, the likelihood function. And in order to do this, you need to take the derivative from this with respect to the p, equalize this to the 0, and find a value for the p, which would maximize this function. Basically, it would tell you, hey, for this value of the p, most likely you are going to obtain this data, which you have. And in our case, it's 30 Hz. So there is a way to do our calculations much more easier by taking the logarithm of the likelihood functions, and this is called the logarithmic likelihood functions, where I'm just going to take the log of this likelihood function. If you take the ln of this likelihood function, it's going to be c 50 30 probability p in the power of 30 1 minus p in the power of 20. So again, we are solving the maximum likelihood estimation problem, right? So the first problem, for the first part of this question, find the likelihood function. This is the likelihood function already. So this is the likelihood function. And we are solving the second problem. Find the maximum likelihood estimate. Basically, find a value for the p, which makes the likelihood function to be maximum. So in order to do this, we are going to take the ln. So we know that for the logarithms, we have the property that we can just expand the arguments of the logarithmic functions, right? We can write it down as the ln of combination of the 50 and 30 plus the ln of p in the power of 30 plus ln of 1 minus p in the power of 20. So this is still a function which depends on p, and actually what I can do is I can take its derivative with respect to the p and equalize this to the 0 and find the value for the p, right? So if I take the derivative from this, so before we do this, I need to still do a little bit simplifications here. So ln of combination of 50 and 30. So the 30 in the power of the p is going to go down. So it's going to be 30 ln of p plus this 20 is going to come back to here. So it's going to be 20 times ln of 1 minus p. So now we can take the derivative from this. We are going to take the derivative with respect to the p and equalize this to the 0. So the derivative of the first term is equal to the 0 since it's a constant. The derivative of the second term is going to be 30 over p plus the derivative of the last term is going to be 20 over 1 minus p. But since inside I've got the function which is a function of the p, not simply a p, I need to take the derivative of this as well. So the derivative of the 1 minus p with respect to the p, it's going to be minus 1. And I need to equalize this to the 0. So, and then I need to solve this for the value for the p. I will give the common denominator. It's going to be 30 times 1 minus p. And this term is going to go to the right, and it's going to be 20 times p. If I open the brackets up, it's going to be 30 minus 30p is equal to the 20p. So this 20p can go to the right, and it's going to be 50p, right? So basically 30 is equal to the 50p. So from here, we can find that the value for the p, it's going to be equal to the 30 over 50 or 3 over 5. So this is the maximum likelihood estimate. And speaking in a human language, it means that for this value of the parameter p, most likely I'm going to get 30 heads when I toss the coins 50 times. So we are going to solve a couple of more problems because our probability mass function might be given differently. For example, this one is slightly different one. So conceptually this is the same, but it will take a little bit more time for us probably to find a solution for this. So let's say x is a random variable. Now it takes the 4 values 0, 1, 2, and 3 with the corresponding probability mass function, where the theta here is the parameter. So the theta is the parameter which we don't know. So this is the unknown parameter. So what we do is, so we wrote down someone wrote a program, and I just run this program and I've got this data. So it generated me 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. And those numbers are 3, 0, 2, 1, 3, 1, 2, 0, 1. And I would like to know, hey, for what value of the theta I would get exactly this data, or most probably I will get this data, right? So in order to do this, I need to find out the probability function, right? So I need to count, hey, what is the probability of getting the 3? It's going to be 2 times 1 minus theta over 3. Probability of getting 0 is theta over 3, and so on. So basically, a probability of getting 3 and then 0, it's going to be the multiplication of their probabilities, right? So basically, first of all, I would like to figure out what is the probability of getting the data exactly in this order. So in order to do this, I just need to multiply the corresponding probabilities. It's going to be 2 over 1, 2 times 1 over theta times over 3 times theta over 3 times 1 minus theta over 3 times 2 1 minus theta over 3, and so on, right? So I will have actually 9 terms here. What I can do is I can regroup them actually, right? Because I have 1, 2, 2, 3. So that's why I can write as 2, 1 minus theta over 3 in the square, because I will have 2 3's appear here. So 1 3, second 3. I will have here, how many zeros I will have? 0, 0, 2 zeros. It means that I can multiply this, the probability of obtaining the 0, theta over 3 twice again. So theta over 3 in the square times. So how many times will have the 2? 1, 2. So twice I will have the 2, so that's why I'm going to multiply the probability of the 2 twice. That's going to be 1 minus theta over 3 in the square. The rest is going to be 1. Probability of getting 1 is 2 theta over 3, right? So the 2 theta over 3 in the power of 3. So this is the likelihood function. So you basically need to denote this as the L of theta. So the likelihood function for this data. So what we need to do is we basically need to find the value for the theta so that this likelihood function will take its maximum value. In order to do this, you again take the derivative, equalize this to 0, but we've seen before that taking the derivative of the logarithm of this function is making our life much more easier, right? So let's take a ln of L of theta and make it and simplify this. So in this case, it's going to be 2 times ln of 2, 1 minus theta over 3, plus 2 times ln of theta over 3, right? So it's going to be plus 2 times ln of 1 minus theta over 3, plus 3 times ln of theta over 3. Okay, so what I can do is I can even simplify this even more, right? I can write this as the 2 times ln of 2 plus ln of 1 minus theta minus ln of 3. So you just basically need to know a couple of properties of the logarithms. Basically tells you that ln of x times y, so it basically tells you that ln of x times y is going to be equal to the ln of x plus ln of y, and ln of x over y, it's going to be equal to the ln of x minus ln of y. Okay, so I'm just using this property and expanding everything. It's going to be plus 2 ln of theta minus 2 ln of 3 plus 2 ln of 1 minus theta minus 2 ln of 3. And the last term is going to be plus 3 ln of theta minus 3 ln of 3. So if you just expand everything, you will have this, like lots of terms with the ln's, right? So what we have to do is we need to maximize it. So that is why we take the derivative of the ln of the likelihood function with respect to the theta. So basically all the terms with the constants are going to just vanish. So this term, this term, this term, this one and this one are going to be just simply deleted because they don't depend on the theta, right? So what is left here is the 2 times ln of 1 minus theta. Its derivative is going to be minus 2 divided to the 1 minus theta. So the derivative of this one is going to be plus 2 divided to the theta. The derivative of this one is again minus 2 divided to the 1 minus theta. So derivative of the last one was the ln is going to be plus 3 divided to the theta. And all of this thing is actually equal to the 0. So this is equal to the 0. So what we have to do is we need to just make the, let me just put these two terms to here, to 0, right? And what we have here is like 5 over theta is equal to the 4 over 1 minus theta. If this term goes to here, this one goes to here, and I will have 5 minus 5 theta is equal to the 4 theta, right? If 5 theta goes to the right, I will have 5 is equal to the 9 theta. So that is why the value for the theta is going to be equal to the 5 over 9. So basically for this value of the theta, I must probably get the sequence of the data. So basically if I plug in theta to be equal to the 4 over 9, so it was 4 over 9 or 5 over 9 to this probability mass function, most probably I will get this data when I generate the new data set. So actually, so we found out here the likelihood function, then we maximize this and found out the value of the theta, which will maximize this. Okay, and the last one is going to be again the similar one. So again, so we obtain a data 2, 4, 6 for this probability density function in this case. And the parameter actually here is the t. So t is the parameter. T is the parameter. And we have to find out the value of the t, so that most likely we are going to get 2, 4, and 6 when we generate the new data using this density function. And again, so we just need to substitute, instead of x, I need to substitute the 2, then 4, then 6. And I just need to multiply them since I need to get 2, 4, and 6. So basically as a multiplication rule. So it's going to be f of 2 times f of 4 times f of 6. And it's going to be our likelihood function, which depends on the parameter t. So it's going to be basically 2t e to the power of minus 2 t over 2. So times 4t e to the power of minus 4t over t times 6t e to the power of minus 6t over 2. And this is our likelihood function, right? So what we can do is actually, so I can regroup the t's. It's going to be 2 times 4, it's 8 times 6, it's going to be 48 times t in a cube, right? And it's also, I can regroup the powers of the e. It's going to be e to the power of minus t, so this 2 can be cancelled, minus t, minus 2t, minus 3t. It's going to be minus t, minus 2t, minus 3t. And this is still a likelihood function. What I can do is, I can immediately take the derivative of the likelihood function and equalize this to the 0 in order to find the value of the t, which will maximize this likelihood function. Or I can take a ln, which is going to give you the same answer actually, but it's much more easier for us to work this out. So it's going to be a ln of 48 plus a ln of t cubed plus a ln of e in the power of minus 6t. So this is the ln of the likelihood function. So what we need to do is we need to take its derivative of the likelihood function with respect to the t, and equalize this to the 0. If you take a derivative, the first term is going to give you simply 0. So the second term, so if this 3 is going to go down, it's going to be 3 over t plus the derivative of this one is going to be, so actually ln of 6 in the power of minus 6t, it's going to be minus 6t, and derivative of the minus 6t with respect to the t, it's going to be simply minus 6. And we have to equalize this to the 0, right? And from here, we need to find a value for the t. It's going to be 3 over t, it's equal to the 6. So that is why the value for the t is going to be equal to the 0.5 or 1 over t. So basically, the maximum likelihood function value is going to be equal to the t is equal to the 1 over t, and this is our likelihood function. So in this lecture, we've learned about the likelihood functions and about the maximum likelihood estimators. So in our next lectures, we're going to talk about the interval estimators.